Good morning, everybody. So for today, if you guys want to go into the reci canvas and pull up under files, there should be a chapter 8 review PDF. We're going to be going through these problems today. So I'm going to give kind of just sort of a short crash course on these, just a little bit of review of what we did today, but most of today is just going to be doing problems. So let's start with these H2 platinum problems. That's kind of a review. If you had an H2 and platinum, you're going to reduce down to an alkene. If you do have enough to have chirality to it, let's say this example here, when you add an H2, it does do a syn addition. So we're going to be reducing this down to, can you make this even more different? No, that's okay. Something that looks like this here. If anyone has having trouble finding the worksheet, I can go through where to find that for a second. So if you go into the regular recitation here, your home page, you click on files on the left here, should be the only file in the box. So we're going to start on this chapter 8 review here. I'm going to give you guys a few minutes to go through these first 3 problems to generate what you think is the correct answer, and then we will talk through them together. So I'm going to give you guys about maybe 3 or 4 minutes, and then we'll start on these chlorination ones after this. So I'm going to go back to my iPad. I'll draw them out while you guys work on them. So see you guys back in a few minutes. All right, so for this first one here, I'm realizing that none of these are actually going to give you any sort of chirality to them, so I'm going to add in a methyl group down here in the second one. We'll throw an extra one in there as an example. So for this first one, because we already have an H here, our final product is only going to give us one chiral center to it. So our products in this would be just this here. It's because you're ending up with two H's at this position. You're not generating chirality in your final product, except for the one that already existed down at the bottom here. Technically, you could draw this as this here, which would also be the same thing as just drawing it as a line. So because you don't generate a chiral center on both positions, this ends up just being losing its chirality, which is why I'm adding a methyl group down here at this one, just to give you an example of where it doesn't. So put this one down at the bottom. If we were to retain our stereochemistry for this, oh man, so rough. Now that I've added a methyl group to this, there are two different possibilities. We could either end up with this product, or this product. With what is actually drawn, I'm going to run out of space a little bit. I'm going to erase this top one. So what's drawn in the worksheet, if you just want the product of that one to double check your answer, that is just going to be this here. You guys end up with two H's at this position. There's no chirality to your product. All right, last one. We already have two H's here, which means we're going to end up with three at this position. So we're definitely not getting a chiral center there. This is just going to be, if I can draw a 7 ring. Why are we able to have it for the second one and not the first one? Ashley, is that what you're asking?
Yeah, that's what I was curious
Okay.
about.
In order to have chirality, you need to have both ends of the double bond need to be tertiary. So like this example here versus this. So when I had add H2 here, there's currently no hydrogens in any of these positions, which means that each of these centers is going to be chiral. They both have 4 unique things on them. I'm not going to number them based on priority. I'm just numbering them. That's for, oh. I have no idea what the heck that was. My fire alarm just went off for a second. That kind of came from the door, so that was odd. Versus on this bottom one here, when I add H2, this is no longer a chiral center. So even though these, like, you could say these H's both added wedge or both added dash, you don't really get a sin product if these are the two that added. Okay, I think they're testing my fire alarms. So technically your product would be like having two dashes and two wedges here. It just doesn't matter because one of your centers isn't chiral. So then it's just I'll end up being a line in the end product. Does that make sense?
Yeah.
So let me draw out both the answers and kind of like. So if this was a dash here. Okay, that's getting annoying. Your other potential product would be nope, wrong one. This where you added these two H's that are starred. Again, this center is not chiral. So really, like a more accurate representation of this, I don't know what the heck's happening out there, would be just a combination of these two. And if you have a 50-50 mixture, you can just draw it as a line. So this just ends up being this. So when you don't have two chiral centers to start out with, you're only going to end up with just basically reducing down to lines.
Okay, thank you.
You're welcome. Okay, so looking at our next four problems, I'm going to kind of skip rearrangements and come back to it when we do the alcohols. So just looking at our normal HCl or HBr, we're going to pick up this H. Versus if we're in peroxide, it's going to go to the opposite center. I just drew it in the wrong center, didn't I? We're in peroxide. This is going to end up adding anti-Markovnikov. And we'll end up with this product. And this is one we'll talk about a lot on Wednesday. But for the most part, you just need to know what product it's going to lead to. So take a few more minutes, go through the rest of the left side of the page, and then we'll review them together. All right, so for these, we're really just looking at a double bond and assessing where's the more substituted end. So we have a tertiary end over here and a secondary one on this end. HCl is going to add to our tertiary end. Or sorry, the Cl is going to add to our tertiary, the H is going to add to our secondary. Giving us this product here. Same thing on the next one. We've got a secondary center and a tertiary center. Our Cl should end up on our tertiary center. H should end up on our secondary. Second half of this, we're in peroxide. So we're going to be doing the opposite. We've already indicated on the top what our primary and our secondary and tertiary centers are. So we know that now our Cl should end up on our less substituted end. So we're going to end up with our Cl at this less substituted position. And then for this last one, same thing. Our Cl is going to end up on that secondary position. Any questions on these ones? Okay, I'm going to jump around a little bit. We're going to do kind of the middle of the second row. We're going to do these H plus H2O ones, and I'm going to talk a little bit about rearrangements. So actually, we talked about rearrangements a lot in depth. I'm going to give you guys a little bit of time to try this one. So this first one should end up pretty straightforward. There's going to be no rearrangements from it. The second one is going to be a bit of a mess. There's going to be two different products. One that's going to rearrange and one that's not. So think about your first step and where your H is adding, and then give that one a shot. So I'm going to give you guys about, I don't know, 4 minutes to try to do these two problems. The first one should go pretty quickly. The second one we'll walk through pretty heavily once we're done. So I'm going to meet you back with you guys, let's say 38, and then we will talk through these two problems. All right, so this first one should be pretty straightforward. We've got a primary center and a tertiary center. We can pick up this H. Going to make a tertiary carbocation. It's next to a tertiary and a secondary center, so there's no reason to do a rearrangement there. Our water can come in. We'll eventually lose that H off of it and make an alcohol. Our second one's going to be a lot more complicated. And one of the main reasons, so someone asked in future quizzes, are you expected to show the mechanism or arrow behind these reactions? It depends on what kind of problem it is. If it's a mechanism, if it's specifically asking you for the mechanism, then yes, but most of the time it's just like a predict the product page, in which case you don't need to. Okay, let's take a look at this bottom one here. So we've got two different centers. They're both secondary, which means they can both lead to a product. So if we have our double bond attack this H, now we're going to have two different realistic possibilities for our carbocation. To be these two. There's no reason why it'll go to one and not the other. They're both secondary, so they both should form. For this one at the bottom, we have a secondary carbocation. It's next to other secondary centers, which means that this is going to lead to just a normal product. Versus this one on the right, it is secondary and it's next to a tertiary center, which means it can do a hydride shift. So it will. And then our OH can come in. Now that we're at the most substituted center it can be at, we'll end up losing that H and end up with our second product, which is where OH is over here. Are there any questions on this problem? Okay, our next couple are pretty straightforward. We're just kind of doing similar to what we were doing with HBr and HBr and peroxide. Could have a different set of reagents now. So if we take mercury acetate and water followed by sodium borohydride, this is kind of like our HBr equivalent. And then the other one is going to be BH3, NaOH, and peroxide. This is going to be our BH3 or HBr and peroxide equivalent. And this will give us our less substituted product. So I think it's like the top two and then going down three, wait, 1, 2, 5, and 6 on the middle column. So go through, do those problems, and then we'll do them together. I'll give you guys a few minutes. I'll write them up here, and then we'll talk through them. All right, so again, assessing our double bond centers. This one is tertiary. This one is secondary. Means our OH is going to add to the tertiary center. We're not in peroxide, so we're doing a normal Markovnikov addition. We're going to end up with an alcohol. Coming off of here. Same thing on our next one. We have a tertiary and a primary. Our double bond is going to end up forming an OH at this more substituted center. Second half, we're in peroxide. We're going to be doing the opposite. They're the same molecules, so should form that OH in your last substituted center, and same thing with this last example, like so. Any questions on these? Okay, I think these ones are pretty straightforward. Let's talk about some brominations. So two different flavors. When you're dealing with BR2, you can either have BR2 or BR2 in water. Let's see. I don't know, do something like this. BR2 is going to always give you a anti-addition. I'm not going to go through the full mechanism. I'm just going to kind of draw one step of it. Eventually, you're going to hit this kind of three-membered complex here. From this point, your BR is going to come in and attack at your more substituted position and do an SN2. Leading to anti-products. For a BR2 and water reaction, it's going to be almost identical. The difference being this last step is going to be water coming in instead of BR. So you'd form this complex. Here, a water is going to come in and attack at your more substituted center. Still an anti-product. Now you just replace one of your BRs with an OH. Okay. So we're going to do the bottom two problems on the second column and the top two on the right column. I'm going to skip those two O's analysis ones and throw them together at the end with the other O's analysis. So take a few minutes to go through these. I'll draw them up on my iPad, and then we'll talk about them together. All right, so we're doing anti-addition of BRs here. As I kind of hinted at or talked about a little bit in class, the easiest way to not mess this up is to keep your same configuration. So we have kind of this trans configuration. If we draw these again in a transform and put them in anti, configuration, this is going to get us easily to our product here. Same thing on the other one. This kind of looks cis, so we're going to draw this in that same cis type configuration, and then put our BRs on an anti fashion. All right, BR2 and water. So we're going to be adding bromine and OH anti to each other. The OH is going to be on the more substituted position. So for this here, we still have a 5-membered ring. Our OH is going to be end up. This is secondary. This is tertiary. Our OH is going to end up in the tertiary position. If it's a wedge, that means our BR is going to be a dash. With a plus minus because that could happen in the other configuration. Last one. We have a primary and a tertiary position. For this one here, so our OH should end up on this tertiary position. BR should end up on the primary. Technically, you don't actually need stereochemistry for this one because you have an achiral center here. So you could just draw this one as OH and BR. It's the same concept as what we're doing with the H2s. Because you don't have two chiral centers, you could really just represent it with a line. Okay, let's do some dialkylation or diol formation. So making two OHs on there. We have two different flavors of that. If we add in either MCPBA or some sort of peroxy acid, in H3O plus, we're going to generate anti-addition of OHs versus if we add in osmium tetraoxide. Ooh, it looks like I actually added a different reagent in this one. So this is a bit of an old worksheet. For the second to last one on the right, we're going to make that also osmium tetraoxide. So when I do this, I'll draw it up and make sure it's obvious. So OSO4. This is going to end up adding these two syn to each other. On this worksheet, there's one that's labeled as KMNO4, NaOH cold. Just treat that like it's the exact same thing as OSO4. We're not going to talk about KMNO4 in this class, but it technically does the same thing. So we are going to do, what is this? 1, 2, 3, 4, 5 and 6 in the second column, 3 and 4 on the third. No, sorry about that. That's wrong. 3, 4, 5, and 6 in the third column. That's what we're doing. And we'll do O's analysis at the very end and get you guys out of here. Okay, so first one is going to be anti-addition. First two are anti-addition. We're dealing with either MCPVA or a proxy acid. MCPVA is a proxy acid, so ROHs are going to end up anti to each other. Same thing in this next one. Technically, you have a tertiary or a primary center, so it's going to end up not mattering. But I'll draw them out as being anti anyways. For our last one, they're going to be syn, our last two. Because we're in osmium tetraoxide. And again, on this bottom one, they would be syn, but because we made an achiral center, you could really just draw them out as lines. Any questions on these? Okay, we're going to quickly talk about O's analysis. So the O's analyze a bond. You're essentially just going to cleave it. End up with two carbonyls. Like so. Our examples are a little bit more complicated, so it is the 1, 2, 3, 4, 5, 6, 7, and 8, and the last one on column 3. So 7, 8 on column 2. The last one on column 3. Go through those. I'm going to give you guys about 2 minutes, then we'll go through them together, and we will be done for today. All right, so we're splitting our alkenes down the middle, generating 2 different, in this case, ketone and aldehyde. We have an intermolecular one for this next one, so we're going to end up with 2 different carbonyls in the same molecule. So 1, 2, 3, 4, 5. So just make sure you have the same number of carbons. When you do this cleavage. For this last one, this one's going to get a little messy because we have double here. We're going to have a cleavage here and a cleavage here. So we would get a carbonyl at this position, the other half of it over here, and then a carbonyl at this position, the other half of it over here. You can draw them pointing towards each other. It's the same thing. Okay, so that is everything I got for you guys today. If you guys don't have any further questions, I will see you guys in lecture tomorrow.
Thank you.
You're welcome.